Hi class, I'm so sorry that I'm not here today to teach you this lesson. I'm still not feeling very well, so hence why you have a video. Here's how today and tomorrow are going to work. Today you're going to take a video on sampling distribution for sample mean. So yesterday we talked about proportion. Today we're going to talk about mean. This is the end of chapter 7. Tomorrow you will do a problem set. Your problem set does not have sample mean on it, so it only has proportion and then the first set of notes. Monday and Tuesday we will review for your test. I will be here Monday and Tuesday, and then your test will be Wednesday. So if we want to just jump right in, we're going to talk about a lot of the same things today that we talked about yesterday when we talked about proportion. We're going to talk about how do you find the mean and the standard deviation of the sampling distribution, how do you know when the sampling distribution is going to be normal, and then we're going to look at a few different problems. So we're going to just jump right in. These notes are on pages 9 and 10. First question, what are the mean and standard deviation of the sampling distribution of a sample mean? So again, when we're talking about a sampling distribution, we're taking every single sample of the same size. And then in this case, we're calculating the sample mean of each sample. So when we graph them, each dot is going to represent a sample mean. You should be able to figure out the formula for the mean of the sampling distribution. So if I take all of those sample means and I average them out, what do you think I'm going to get? Well, I'm going to get the population mean. That's similar to yesterday. Yesterday, when we averaged out all the sample proportions, we got the population proportion. Again, this is because sample mean, like we talked about yesterday, is unbiased. Now, standard deviation formula. Similar to proportion, when you're taking bigger samples, your standard deviation goes down. So if I want to take all of those sample means and then take the standard deviation of all of them, that's going to be the same as the standard deviation of the population divided by root n. So again, I think we get confused on the symbols a lot, so make sure you're paying particular attention to what those symbols mean. Are these formula on the formula sheet? Yes, they are. So by the formula sheet, I mean that blue cardboard or cardstock packet that I gave you at the beginning of the year that we used for normal tables. Like I said yesterday, you can't use that on the test, but you can use it on the final and all of second semester. Are there any conditions? Yes, there are. Just like yesterday, there's a condition for the standard deviation formula. Either you are going to be sampling with replacement, which we said yesterday is not very realistic. We're rarely, if ever, sampling with replacement, or your sample size has to be small relative to the population. So same thing as yesterday. So this should look really familiar. This is pretty similar to what we did yesterday. If we're talking about interpreting standard deviation, it's the typical deviation from the mean. So if we were to take a whole bunch of x bars, the standard deviation would be the typical deviation of those x bars from mu, from the population mean, which is something that's really important to know. We want to know if we take a sample, about how far should we expect to be from the population mean. Now, what is the shape of the sampling distribution of a sample mean when the sample is taken from a normal population? Okay, if you have a normal population, then the sampling distribution is also going to be normal. Does the sample size matter? No. So if I have a normal population and I'm told the population is normal, and I take samples from it, the sampling distribution will be normal, regardless of what size samples I take. So I take samples of size 5, 10, 20. Regardless, my sampling distribution is going to be approximately normal. That's not necessarily the case if the population is not normal, though. So we'll get to that eventually. So right now, we're going to do an example before we talk about what happens when the population is not normal. At the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of the weights in the jar is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. A. Without doing any calculations, explain what outcome is more likely, randomly selecting a single jar, finding that the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average content weigh less than 16 ounces. Okay, for a few things that I want to look at. I want to talk about X, which X is going to be the weight of a single jar. I'm just defining that to be. So X bar then is going to be the average weight of 10 jars. Okay, X we already know from the problem is a normal distribution. Right, it says the distribution of weights in the jars is normal. We know that the mean is 16.1, standard deviation is 0.15. Okay, so what's going to be more likely? One jar less than 10 or an average less than 10? Well, it's certainly going to be a single jar. If we start thinking about 10 jars, that's going to be X bar. X bar, because of above, is going to have a smaller standard deviation than X will. So if we look at the distribution of X bar we also know is normal, and that's because our sample is taken from a normal population. We know that the mean is still going to be equal to the population mean. Standard deviation is not, though. The standard deviation is going to be it's going to be exactly 0.15 divided by root 10. That's the formula that we did above. Now, if we have a smaller standard deviation, that means it's less likely to deviate from the mean. So below 16.1, deviating from the mean is certainly going to be more likely in this first case. And to prove that, we're actually going to find the probability of each event. So for a single jar, we are looking for the probability that X is less than 16. Like we said above, we know that X is normal, we know the mean, and we know the standard deviation. So we're going to convert this to a z-score. So it's going to be 16 minus the mean divided by the standard deviation. You should know how to do normal CDF on this. So I'm going to tell you I already did it for you. You end up with a probability of 0.252. So we're going to say that that's more likely than in the case of taking a sample. Okay, be careful to your notation here. We want to find the probability that a sample of jars has an average less than 16. So we want the probability that the average X bar is less than 16. As soon as we talk about X bar, that now means that we need to use the distribution of X bar. So again, converting this to a z-score, it's going to be 16 minus 16.1. What changes, though, is that standard deviation. Again, you would do normal CDF for this, but I already did it for you. And you get a probability of about 0.0175. So it is much less likely to find a sample that's less than 16 rather than just a single jar. So this should look really similar to what we did yesterday. Now, in this case, a few differences from yesterday. First one, we automatically knew that X bar was normal because the population is normal. So there wasn't an additional condition that you had to check. Yesterday, we did check the 10% rule, which I didn't check here, but we should be checking. You need to make sure that you are checking the 10% rule. 10% rule allows us to use that standard deviation formula. So in this case, if we're taking a sample of size 10, we need to be assuming that there are more than 100 of these jars, which I think is pretty reasonable to believe if we're looking at Peanut Company, that they have more than 100 jars. I don't have enough room, but in your homework, in your problem set, I would expect to see you check the 10% rule. And then, of course, because these are normal distributions, we should be drawing normal curves, except, again, I don't have the room for that, so we're not going to check. These are the most commonly missed problems, or one of the most commonly missed problems for students. And why? What are their errors? Well, the biggest error is that they don't divide the standard deviation by the square root of n. So a lot of times in the sample problem, they'll just divide by 0.15, forgetting that root 10. Now, why would they be doing that? Why would they forget the root 10? It's not just a mistake of forgetting the root 10. A lot of times, students don't recognize that they're looking at a sample. So they'll treat a problem like it's a single individual, like in our first problem, as compared to a sample. So So you need to be reading the questions very carefully. As soon as you see a sample, that's when we need to start thinking about x bar, not just x. Now, what some students will do is they'll take that 0.252 probability and they'll raise it to the 10th power. That's not the probability that we're looking for. If you do that, what you're doing is you're finding the probability that all 10 jars are less than 16, not an average less than 16. So we need to be careful about the wording and really think about our calculations. So then the next logical question that comes up is, well, what happens if we have a population that's not necessarily normal? Is our sampling distribution going to be normal? So that's what we're going to talk about next. Okay, so the next question, what is the shape of the sampling distribution of a sample mean when the sample is not taken from a normal population? Does the sample size matter? Yes, it does. So this one is really important. In the case where you have a sample size that is greater than 30, x bar will be approximately normal. So if you are taking a whole bunch of samples that are bigger than 30, your sampling distribution will be approximately normal. In the case where your n is not 30, x bar's shape will follow the population shape. Okay, so the only probabilities we know how to do right now, and that really we're going to focus on for the rest of the semester, or the rest of the year rather, are normal distributions. So we really only care about case 1. So we care about your population's not normal, but you're taking samples that are pretty big, therefore your sampling distribution is approximately normal. This is really important, and it does have a special name. This is called the central limit theorem. Those cases where you have a population that's not normal and you're taking small samples, we're not going to look at that. So we're really only going to look at case 1. So we have one more problem to do and then a few other things to talk about, and then you guys will get to work on homework. Okay, so next problem. Suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assume that students at your school are typical texters and that you randomly select 50 students from your school. A. Calculate and interpret the standard deviation of the distribution of x bar. Okay, so for A, I want to write down what we know. We know that our population is skewed right. We know that the mean of the population is 15. The standard deviation of the population is 35. And we know that we are taking a sample of size 50. We want to calculate and interpret the standard deviation. Okay, so we want the standard deviation of x bar. Oops, sorry, wrong symbol. So we want the standard deviation of x bar. That's going to be the standard deviation of the population divided by root n. So in this case, 35 divided by the square root of 50. Okay, we need to interpret this. This is typically how far, in the long run, if I take a whole bunch of samples of size 50, this is typically how far that sample mean is going to be away from the population mean. So again, if I take a whole bunch of x bars, a whole bunch of samples of size 50, this will be the typical deviation from the sample mean to the population mean. Now, there is a condition that we ignored. We haven't checked the 10% rule yet. So in order for this standard deviation to be valid, our sample size has to be less than 10% of the population size. In this case, we don't know how many students there are at this school, so we need to solve for that. N has to be greater than 500. Now, we have no idea what this school is, how many students it has, so we're just going to have to assume that this is reasonable. And I need you to write that for me. It is reasonable to believe there are more than 500 students at this high school. Now, we're just going to have to assume that. We don't have enough information to really know whether or not this is true. We don't know if it's a large high school. We don't know the population size. So we're just going to have to assume that that's the case. B, what is the probability that these students have sent more than a total of 1,000 texts in the last day? Okay, so we've been talking about X bar, so we really need this in terms of X bar. If the students have sent 1,000 texts and there's 50 of them, that's an average of about 20 a day. So really we're looking for what is the probability that this group has an average of more than 20 in the last day. Okay, well we need to know the distribution of X bar. X bar is going to be normal. The mean of X bar is the same as the population mean, which is 15 rather. Standard deviation is what we already calculated. It's at 35 over the square root of 50. Now, how do we know that X bar is going to be normal if the population is not normal? Well, X bar is normal by the central limit theorem. We took a sample size that was bigger than 30. So because we're taking samples of size 50, if we took a whole bunch of samples of size 50 and we graphed them, the distribution would be normal, the sampling distribution. Now, since we have a normal distribution, we can convert this to a z-score. So this is really the probability that z is greater than 20 minus 15 all over 35 divided by the square root of 50. Again, you're going to use normal CDF. This ends up being about 0.1562. You should be drawing a figure. We didn't draw a figure because I don't have enough room. A normal figure, that is. Okay, so comparing mean, sample mean, and sample proportion, the two distributions we talked about yesterday and today. Proportion is very straightforward. Mean has kind of those two different cases, if your population is normal versus when it's not. So we need to be considering the central limit theorem. What I want to do real quick is I want to make sure that we know what each of these symbols means. So we're going to go over them. Mu is the population mean. Sigma is the population standard deviation. P is the population proportion. N is the sample size that you are taking. X bar is the sample mean. P hat is the sample proportion. And then these last four, those relate to the sampling distribution. So if I found every single sample mean, or the sample mean of every sample, or if I found the sample proportion from every sample and I graphed them, that would be the mean and the standard deviation of sample mean. That would be the mean and the standard deviation of sample proportion. So it's very important that we pay attention to those symbols and that we use the correct symbols and that we know what they mean. Last thing, I want us to compare and contrast the distributions of p hat and x bar. Specifically, we care about shape, center, spread, and any conditions. So I'm just going to make a table. Left side, I'm going to talk about p hat. Right side, I'm going to talk about x bar. For shape, our distribution for p hat is going to be normal if our two inequalities hold true. So if np is at least 10 and n1 minus p is at least 10. For x bar, we're going to be normal if population is normal or our sample size is bigger than 30. So that one's the one that's harder to remember because you have kind of two different cases. Center, so what I mean is the mean of all of those p hats. So if I found all of the p hats and I average them, I'm going to get the population proportion. If I found all of those x bars and I averaged them, I'm going to get the population mean. For spread, if I found all of those sample proportions and then I took their standard deviation, that would be the square root of p times 1 minus p all over n. Over here, for sample mean, if I found all of those sample means and then I found their standard deviation, it's a population standard deviation over root n. And last thing, for conditions, they both have the 10% rule. So you're going to have to check that for both distributions. Or you're sampling with replacement, which we said is not very reasonable. So you should be able to see that what we learned today is pretty similar to what you learned yesterday. It's just looking at mean instead of proportion. So what you're going to do now is you're actually going to be working on the day 5 homework. Day 4 homework is the problem set. So tonight is the day 5 homework. Tomorrow you'll do the problem set in class. Whatever you don't finish will be homework, and then we'll grade the problem set on Monday. Please make sure if you have questions that you are writing them down so that you can ask me when I come back on Monday.